A maths teacher decides to surprise her class with a probability test, and it's a multiple choice test, but because the students haven't revised, they just guess all of the answers. In each question they have a choice of A, B, C, D or E. So one student answers as follows. What score would you expect the student to get? Well, here are the answers, and you can see that the student got 4 of her answers correct. So she receives a score of 4 out of 20. Now, if each of the students in the class did the same thing, how many of the students would you expect to receive a score of 0, or 1, or 2? How many would you expect to achieve a score of 20 out of 20? Have a think, and then during this lesson we will explore the mathematics that will help you to predict these answers. Here's a probability question involving 3 red and 2 blue discs in a bag. 2 discs are chosen without replacement. The probability of choosing a red disc second, given that we chose a red disc first, is 2 out of 4. So the probability of choosing 2 reds is 6 out of 20. Probability of choosing a red followed by a blue, 6 out of 20 again, 6 out of 20, 2 out of 20. Now, if we just consider the number of reds selected each time, the probability of selecting 0 reds is 0.1. The probability of selecting 1 red is 12 out of 20, or 0.6, and the probability of choosing 2 reds is 6 out of 20, or 0.3. This is called the probability distribution for selecting different numbers of red discs. And we introduce a variable for this, so we let x represent the number of reds selected. And x can take different values, specifically 0, 1 or 2 in this case. So the probability that x equals 0 is 0.1, the probability that x is 1 is 0.6, and the probability that x equals 2 is 0.3. Now, because x is a variable and it's chosen randomly and it can take only certain discrete values, x is called a discrete random variable. Another example of a discrete random variable is x when we define x to be the number of heads obtained when we flip a fair coin 3 times. And you can see that there are 8 outcomes in our sample space. But just considering the number of heads obtained each time, the probability that x equals 0 is 1 out of 8. To obtain 1 head, that's 3 out of 8. To obtain 2 heads, also 3 out of 8. And to obtain 3 heads is just 1 out of 8. So the probability that x is less than 1 means that x must be 0, is 1 out of 8. The probability that x is greater than or equal to 2 means that x is 2 or 3, 4 out of 8. We can also look at cumulative probabilities. So this would be a table of probabilities for x. This would be a table of cumulative values of those probabilities. So the probability that x is less than or equal to the different values x can take. So for 0, it's 1 over 8. Less than or equal to 1 is 4 out of 8. Less than or equal to 2, 7 out of 8. And less than or equal to 3 is 8 out of 8. The final value should be 1. When we give a table of probabilities, we're showing that the total probability is 1, and we're showing how that 1 is distributed amongst the possible values of x. So in the previous example, we had probabilities of 1/8, 3/8, 3/8 and 1/8, totaling 1. This is called the probability distribution for x. The possible values x can take must be exhaustive, which means that we include all of the possible values. In the case of flipping 3 coins and counting the number of heads, the possible values are 0, 1, 2 and 3. They must also be mutually exclusive. So when flipping a coin 3 times, you can have 0 heads, or 1 head, or 2 heads, or 3 heads, but you can't have more than one of these values at the same time. Now, because each value x can take is assigned a probability value, the pairs together form a probability function, and so we can use the notation f of x to represent the probability that x can take each different value. We can also state cumulative probabilities, as in the previous example. Now, going back to that notion of a probability function, we can give the values as ordered pairs. So in the example with the 3 coins, we could give the ordered pairs as 0, 1/8, 1, 3/8, 2, 3/8, and 3, 1/8. Those are ordered pairs. We normally represent them in a table, but in the next example, you're going to see how we can just give the rule as f of x and use that to work out different probabilities. Finally, we can represent probability distributions graphically using a vertical bar graph or a probability histogram. Examples of graphical representations of probability distribution functions for the situation with the 3 coins and counting the number of heads can be seen here as bar graphs, probability histograms, and also cumulative probabilities of the same event. This is an example of a probability distribution where we are given a function to work out the different probabilities for the different values of x. The function is given in terms of x and also an unknown constant k. So firstly we'll work out the probabilities in terms of k, and then we'll try and work out that value of k. So when x equals 1, 6 take 1 is 5, so this is 5k. When x equals 2, 4k, and so on. Now we don't stop there because we know that the total of all the probabilities must be 1. 15k equals 1, which means that k must be 1 over 15. So now we can complete our table with numerical values for k and use these values to work out the answers to the questions. So firstly, the probability that x is even means we're looking at when x is 2 or 4, so that's 6 over 15. And the probability that x is greater than 3, that means when x is 4 or 5, so that's 3 out of 15. This time we have a spinner and we have the values of 1, 2 and 3 on the spinner and associated probabilities. The probabilities need to total 1, so our k value is 0.2. In part B, we're asked to find the probability that we spin a 2 followed by a 3. We're presuming that these spins are independent, so we can multiply the probabilities together. So probability of getting a 2 followed by a 3 is 0.06. Probability of a 2 and a 3 in any order, it's the answer to the previous part plus 0.06, so 0.12. Probability that we get a total of 4, we could have a 1 followed by a 3 followed by a 1, or a 2 followed by a 2, 0.29. And then in the final question, it's a conditional probability. So what's the probability that we get a 2 on the second spin, given that we scored a total of 4? So we already know the probability of scoring a total of 4 is 0.29, and of the 3 options, only one of them has a 2 on the second spin, so that's 0.09. And we simplify this just to remove the decimals within our fraction, so it's 9 out of 29. Finally, we're given a context and we're asked to determine a probability distribution for x, where x is defined as the number of faulty components in a selection of 4. So x can take the values of 0, 1, 2, 3, or 4. Now the probability that any single component is defective is 5 out of 100. You can imagine a tree diagram. The first one you choose is either faulty or not faulty, and then the second one you choose is either faulty or not faulty, and then the third one you choose is faulty or not faulty, and then the fourth one is either faulty or not faulty. So the probability that none of them are faulty means that we're multiplying along the not faulty branches. So the probability that x equals 0 is 95 out of 100 multiplied by 94 out of 99 multiplied by 93 out of 98 multiplied by 92 out of 97. And if you check this on your calculator, you see that you get a value of 0.8119 to 4 decimal places. The probability that all 4 are defective is 5 over 100 multiplied by 4 over 99 times 3 over 98 times 2 over 97, which is 0.0000 to 4 decimal places. If you check on your calculator, it's actually 0.000001. What about the in-between values? The probability that x is 1 is, well, if we imagine the first one we pull out is faulty, that's 5 over 100, and then the rest of them are not faulty. But of course it might be the second one that's defective, or the third one, or the fourth one. So we can multiply this by 4 to show that the defective component could be the first, second, third, or fourth to be drawn out. And again, if you check on your calculator, that gives a probability of 0.1765 to 4 decimal places. Similarly, the probability that x is 3. This time, we only have one component that's not faulty, so that could be the first one, but then the remaining 3 are all faulty. But the not faulty component could be the first, second, third, or fourth component to be drawn out, so we can multiply that by 4, 0.0002 to 4 decimal places. Finally, the probability that x is 2, so we've got 2 faulty and 2 not faulty. Because we've got 2 faulty components, they could be in 6 different positions: first and second, first and third, first and fourth, second and third, second and fourth, or third and fourth. So we can multiply this by 6. And again, check on your calculator to see that it is 0.0114 to 4 decimal places. A quick check at the end would be to add up these probabilities and make sure that they do total 1. The total number of ways of selecting 4 components from the 100 is 100 choose 4. Now, if we want to know the probability that there are no faulty components, then from the 5 faulty components, we're choosing none of them, and from the remaining 95, we're choosing 4 components. So this is our numerator, and the denominator is the total number of ways of choosing the 4 components. Similarly, probability that we have 1 faulty component is 5 choose 1 multiplied by 95 choose 3, and so on. So check these values with your calculator to make sure that we do get the same probabilities as before, and we could express our probabilities using a function. So the probability that x equals a particular value of x is 5 choose x multiplied by 95 choose 4 minus x all over 100 choose 4. Strictly speaking, the probability function should be written in this format. So we're defining the probability that x equals particular values for x as 5 choose x times 95 choose 4 minus x all over 100 choose 4 for these specific x values 0, 1, 2, 3 and 4, and the probability is 0 for all other values of x.